Does anyone have any questions about anything before we start? Alright, so we finished up chapter 3 last time, so we're continuing here with chapter 4. We're going to learn about how to name compounds, and then we're going to move into looking at the energy of compounds as they rotate around in space, so we can get a sense for what these structures actually look like, and that's where it's going to be especially helpful to have models. Leading up toward understanding individual molecules in detail so that we can later start to look at how those molecules interact with one another and undergo chemical reactions. So we really need to build the foundation of the properties and behavior and shapes of individual molecules first, so we can build from that forward. So this first bit of material about molecules specifically, we're going to focus on hydrocarbons. Those are the simplest type of organic compounds, and then later we'll look at what happens when halogens like chlorine and bromine are added, or when oxygen is added, or nitrogen, and how that affects the shapes and behavior of the structures and the reactions that they'll undergo. So for now, we're trying to keep things as simple as possible. Hydrocarbon, the word simply implies the molecule is only made of hydrogens and carbons. No other atoms are present. You can have single bonds for all of your atoms. You could have a double bond or a triple bond. You can also have an aromatic or a resonance stabilized ring. So compound, that specific six-member ring is called benzene, and compounds that build off of that by making more bonds to maybe more carbons and things like that are derivatives of benzene. Those are very common due to the resonance that we talked about before, where the electrons move around. So there's a variety of different hydrocarbons that exist. Some of them are saturated and some are not. So in the context of this type of discussion, the word saturated has a similar meaning to what we saw in general chemistry, but it's a little bit different. So in general chemistry, we said saturated means, in an example where you have a solution, like with a liquid solvent, like maybe water or something like that, and you're adding a solid and dissolving it until the solution is saturated. That means the solution is dissolving as much solid as it possibly can. If I add any more, it wouldn't be possible to dissolve it. So something is saturated when it's holding as much as it possibly can. When we're talking about hydrocarbons, if we're talking about a hydrocarbon being saturated, we're talking about it being saturated with hydrogen atoms. Right? So if a carbon has the maximum number of hydrogens it can possibly hold, just like a solution is saturated when it has the maximum amount of solid it can possibly hold, a carbon-carbon bond or area of a molecule is saturated if each carbon has 4 single bonds and as many hydrogens as it can hold. I can't put any more hydrogens on here because I can't make any more bonds around the carbons. 4 bonds is the maximum bonds a carbon can make, so that's fully saturated. The other 3 compounds here are not saturated. Any compound that has a pi bond has at least the potential for that pi bond to break and for hydrogens to come in. That particular reaction would convert this unsaturated hydrocarbon into a saturated carbon by bringing in the maximum number of hydrogens that could possibly bond to that carbon. So as is, it may look saturated because I can't form any more bonds. Each carbon still has 4 bonds, including the pi bond. But an unsaturated molecule has the potential to break its pi bond. Pi bonds are not nearly as stable as sigma bonds, right? Because in a pi bond, the electron cloud is above and below the plane of the nuclei, versus in a sigma bond, where the electron cloud is primarily putting the electron density right between the nuclei. So these electrons in a pi bond, which are above and below the plane here, they don't really attract that well to the carbon nucleus. So the pi electrons are susceptible to breaking out of that bond and instead existing in a sigma bond with two new hydrogens that might come in. The sigma bond's more stable because it involves head-on overlap between the two atoms, and the electrons get right between the nuclei for the most part when that sigma molecular orbital forms. So any compound that has a pi bond is going to be unsaturated because there's a potential to break that and bring in more hydrogens and form more sigma bonds. Even the pi bonds in this ring make it unsaturated because every one of these could break and hydrogens could come in and replace that double bond with two new sigma bonds. And so that's a really nice example of how to go from an unsaturated compound to a saturated compound. Cyclohexane is saturated. It has two hydrogens on every carbon. Every carbon has 4 sigma bonds. That's the most that can be existing there. So first we're going to look at saturated hydrocarbons since those are the most straightforward. We're looking at a situation where we have some number of carbons and hydrogens. Every carbon, even though they're not always shown, will have a maximum number of hydrogens connected to it to make 4 bonds for every carbon. Each individual molecule that's unique must have its own unique name. So we're going to talk about the naming system that this international group of chemists came up with. It's a systematic system that will help us develop names for compounds and keep our compounds that are unique straight from one another. So if it's saturated with hydrogens, meaning there's no double or triple bonds, the general classification of those molecules is that they are called alkanes. And the ane suffix specifically communicates that the hydrocarbons are saturated with hydrogens. The difference between different saturated hydrocarbons is going to be the number of carbons and or the possibility of branching, right? So if I have 5 carbons, 1, 2, 3, 4, 5, that compound has 12 hydrogens, just enough hydrogens to make 4 bonds on every carbon. I could also imagine bonding 5 carbons together in something like this format, right? That still has 1, 2, 3, 4, 5 carbons. And if I put hydrogens on each one of those that doesn't already have 4 bonds shown, I would still have 12 hydrogens. So C5H12 is a saturated hydrocarbon, whether the carbons are shown in a chain, extended, or whether they're all branching off from one site. The relationship between those two compounds is that they are isomers. Clearly the connections between the carbons and hydrogens are different in pentane versus this neopentane molecule or this branched isomer of pentane. Either way though, the suffix ane indicates that all the carbons in the chain have as many hydrogens as they could possibly hold, or that it's saturated. So there are lots of organic compounds. Many organic compounds have structures that are too complicated to really name easily with the naming system that we're going to learn. So many of them still go by their old names that they were known by before the naming system was developed, especially when you have very complicated structures. So you can see here it's very complicated fused rings together, lots of different atoms. Every time we introduce an oxygen or a nitrogen, that's going to change how we name the compound. Anytime we introduce a site of unsaturation, a double bond or triple bond, it's going to change how the compound's named. So if you were to name this compound using the standard system, its name would be extremely long and complicated, and it's just much easier to call it by its common name. And so that's true for a lot of compounds. So you want to be aware that the naming system we're using is used often for relatively simple small molecules. When your molecules get extremely large and complicated, or if they're very common and the common old name is just used a lot more often, you might not see them named by the IUPAC name that we're going to learn the system for. But the IUPAC system is still useful. It's been around for a while. It's been updated and modified in the meantime. And it is better than having to memorize individual names for every single molecule that might exist. There are thousands and thousands and thousands of molecules that exist. And so many of them, instead of memorizing their names, all we have to do is learn the rules for a system of naming. And once we know those rules, we can apply them to lots of different molecules and communicate about molecules. So this was even more important a while ago before computers, because chemists would often type out the name of compounds. It was much more difficult to draw out a compound by hand and make it look nice and neat than it is now. So for the most part on exams in this course, you'll be dealing with pictures of structures like bond line structures, but I might also give you a name of a compound or expect you to determine the name for a compound. So you want to familiarize yourself with the system and practice it a lot until it becomes kind of second nature for you. So the rules for naming compounds. So this is, again, we're just going to learn the most basic rules right now for molecules that only have carbon and hydrogen, and there's no double or triple bonds. Every carbon has only single bonds, so they're fully saturated with hydrogen, so we're looking at saturated hydrocarbons. So the first step in the process of determining the name for this compound is to find the so-called parent chain. And the parent chain is the longest chain of consecutively connected carbons. So for example, I can start on one end and start numbering in. Right? So I could, through trial and error, try to find a number of different chains here. If I start here and number this as carbon 1, and then go to 2 and 3, 4, 5, 6, 7, I find a chain that's 7 carbons long. I want to keep going until I find the longest chain of consecutively connected carbons. So if I start here, I can get a longer chain, 3, 4, 5, 6, and then this is a little bit longer down here than this is over here. So I want to keep numbering into wherever the longest chain is, and that's how I come up with 9 carbons for the longest chain, right? So I can't jump from 9 and then go over here and number 10, right? They have to be connected with a bond, right? So I'm looking for the longest chain of carbons that are all connected through bonds. That's my so-called parent chain. Any carbon that I didn't get a chance to number, or a grouping of carbons that I didn't get a chance to number, I have to take care of later in the process of naming. So this is just step one. I'm just going to number or count how many carbons I can find in a consecutive chain and find the longest chain possible. Once I know how many carbons are in the longest chain possible for that structure, I want to look up the prefix. It should be on your formula sheet, so you don't have to memorize these, but there are prefixes that match up with the number of carbons in the chain. So if I have 9 carbons in my chain, the prefix is known. And the suffix is going to be ANE, because that implies that all my carbons are saturated. I don't have any carbons that have double bonds or triple bonds. They all have a maximum number of hydrogens that they can hold. So while you don't have to memorize these, you're probably going to work with them a lot, and so the more practice you do, the more you'll remember the prefixes for the first 10. Those are the ones we'll be using most often. Anything beyond 10 might be rarely used, and I wouldn't expect you to probably know those. So you could access the formula sheet, or I might give you that in person if it were necessary for an exam. Alright, so finding the parent chain. Sometimes there's more than one chain that has the same number of carbons, so we need a rule to account for those situations. So here's an example to illustrate that. Right, so this is my compound. I got this bond line representation here. Try again. So there's a couple different ways I can count the longest chain of carbons here, and they're both shown here. So one would start here and numbering in this direction, 1, 2, 3, 4, 5, 6, 7. I can find a 7 carbon chain there. The other possibility is if I start in the same place and go 1, 2, 3, 4, 5, I could have gone down here 6 and 7. So there's this one, and then there's the other one. got two options, so how do I know which is correct? So if that happens, what you want to do is to find the longest chain that allows for the greatest number of substituents attached. That's the key there. So when I number 1, 2, 3, 4, 5, 6, 7 in this format, I get 1, 2, 3 substituents that are not 3 groupings of carbons that are not part of that parent chain of 7 carbons. So if it is 7 carbons, its prefix is hept, and the suffix is ane since there's no double or triple bonds. So it'll be heptane. That's just the name for this parent chain. So I still have to talk about the rest of the naming system and how I account for the substituents. But if you run into a situation where there's multiple ways to name the parent or multiple ways to number the carbons to create a maximal number of carbons in a chain, which is 7, this would also give me heptane as my parent chain. But this one only gives me 1, 2 side groupings of carbons that are not part of that parent chain. So that's not the correct way to number. These 7 carbons don't constitute the parent chain for this molecule. These 7 carbons here do. So if it comes down to it, and there's multiple options for numbering the parent, select the option that gives me the longest chain. If both options give the same length, in both cases we had 7 carbons consecutively, select the chain that creates the greatest number of side groups, because the smaller the number of carbons in the side group, the easier it is to name, and that makes the whole thing a little bit easier. So that's the rule in situations where you have multiple ways to find the most carbons consecutively connected in a parent chain. Sometimes your parent chain will involve a ring. If that happens, all you have to do is pop in this prefix in front of the molecule, right? So if I had propane, prop means 3, right? So 3 carbons in a chain is prop. If there's no double bonds or triple bonds, it's all saturated, it's propane. So normally, if I just drew the structure of propane, it would just be 3 carbons. 1, 2, 3. So that's propane. I can also draw propane like this. 1, 2, 3. Or like this. 1, 2, 3. Right, as long as I've got 2 lines that intersect, where they intersect as a carbon and where they end as a carbon, right? That's the way we communicate with bond line structures. However, if carbon 1 and 3 are connected, I need a different name because it's a different structure. It actually even also has a different formula. If I draw in all the hydrogens here, it would be C3H8. Here, since I connected 1 and 3, there's only space for 2 hydrogens on each carbon. So it's still saturated with hydrogens, because the way the carbons are connected, I can only put 2 on each. I can't put any more than that, and there are 2 on each already, so it's fully saturated. But it has a different formula from the other structure. So propane and cyclopropane are not isomers. They're just totally different because they have totally different formulas altogether. But if it's connected in a ring, I add the cyclo prefix. So 3-membered ring, cyclopropane. Bute is the prefix for 4 carbons, so 4-membered ring, cyclobutane. 5-membered ring, the prefix for 5 is pent, so cyclopentane. Alright, so let's get some practice here with this first step. So we're still only on the first step of the process. We're finding the parent chain. So I might start on the left-hand side, might start on the right-hand side. Doesn't really matter too much at this point. But I want to find the longest chain of carbons in this structure to find its parent name. So I know that this 2-carbon group here intersects at this carbon where this 1-carbon group intersects. So if there's 2 up here and only 1 down here, I'm going to get a longer chain if I start numbering through the more extended grouping of carbons. So I might start here, 1, 2, 3, 4, 5, 6. And at this point, if I go 7, 8, or if I had gone 7, 8, it doesn't really matter because it's equivalent either way. So 8 carbons is the maximum number, so my parent chain is octane. The prefix for 8 is oct. The A and E suffix communicates that it's a hydrocarbon with no double or triple bonds, and everything is saturated with hydrogens. So if I found my longest connected consecutive carbons in a row, 1 through 8, these other groupings that didn't get included in that numbering also need to be included in the name. So again, we're not worried about that quite yet. We're just focusing on what the parent chain is. What's the parent chain over here? Well, when you're finding your parent chain to name this compound, if there's a ring, the ring and only the ring must be your parent, or the entirety of the ring must be a substituent or side group from the parent. So if I number this 1, 2, 3, 4, 5, 6, 7 carbons, that's the most carbons I can get connected together. That would be cycloheptane. Hept means 7. So I got the cyclo to account for the fact that it's in a ring. I got the hept to account for the fact that there are 7 carbons in the ring. And the A and E suffix showing that there's no double or triple bonds. I could have looked over here. So if I were to think about this one a little differently, I could have numbered 1, 2, 3, 4. Then I could have just named this whole thing as a substituent, but again, when we're finding the parent chain, we want to find the longest consecutive chain of carbons connected. So only 4 in a row is not as long as 7, obviously, so cycloheptane should be the parent here. One mistake you definitely want to avoid: don't include some of the carbons from the ring as well as carbons outside the ring all in the same parent. The naming system cannot account for that properly. So if I did start numbering out here and I went 1, 2, 3, 4, and then like 5, 6, 7, 8, 9, 10, 11, I can find an instance in this molecule where there are 11 carbons in a row, all connected. So when we talk about the parent chain, and we're finding the longest consecutive chain of carbons, we have to add to that. We have to say it cannot include both carbons in a ring and outside the ring. It has to be one or the other. So let's say I've got this situation here. Let's say I've got a 5-membered ring, and then off the ring I've got a bunch of carbons. So if I am trying to find the parent chain here, I can either count the ring as my parent or all the carbons outside the ring. I can't include both in my parent chain. So if I consider the carbons in the ring, I would have 1, 2, 3, 4, 5 would be the most in a row I could get. If I'm looking at the carbons outside the ring, I have 1, 2, 3, 4, 5, 6, 7. So if the longer of those is the chain outside the ring, then that'd be my parent. I can't include both. The naming system doesn't allow for that in any way. So it's got to be one or the other. So make sure you follow that rule. Alright, so that was step 1. Hopefully now in any structure I give you, you can find the parent chain, the longest consecutive chains of carbons that does not include carbons in both a ring and outside a ring at the same time. Once you have the parent chain, the next thing you want to do is to look for substituents. So substituents are any groupings of carbons that aren't counted already in the parent. Right? So in this parent chain, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got 10 carbons. So the prefix for 10, like 10 years is a decade, the prefix is dec. There's no double bonds in there, so it's decane. It's a saturated hydrocarbon. So the parent chain is decane. Just writing the name decane accounts for those 10 carbons. But the molecule has more than that. It has these substituents or side groups that are attached to it. So I have to name them separately and then list them in front of the parent in the full name of the structure. So step 2, after I find the parent chain, step 2 is to just identify the substituents. And the substituents' names will depend on how many carbons they have, just like the parent name did. When I name the parent, I put the ane suffix on it to communicate that this is a saturated hydrocarbon. When I name a substituent, I use this YL suffix instead of the ane suffix. So decane means I've got 10 carbons in my parent chain. Here I've got 1 carbon in my substituent. So that would be meth, because the prefix for 1 carbon is meth. I wouldn't put the ane suffix on it though, because it's not part of my parent chain. It's a side group. So I use an YL suffix. So that's a methyl group, or a methyl substituent. 2 carbons is eth. And again, it's not part of my parent chain, so I'm not calling it ethane, I'm calling it ethyl. And then 3 carbons is prop. It's not propane. Propane would just be where my parent chain has 3 carbons. I've already numbered and named my parent chain. This is a side group hanging off of that parent chain, bonded to carbon 5 here of the parent. So propol. Propyl is the name of that 3 carbon, 1, 2, 3 carbon side group. So I want to name my substituents. That's step 2. Let's look at some more examples, just illustrating step 2. So here I find 1, 2, 3, 4, 5, 6. My parent chain has 6 carbons. None of them are unsaturated, and it's a ring. So my parent is called cyclohexane, and there's a 1, 2, 3 carbon group hanging off of that, and so that's a propyl. Right, so the 3 carbon group hanging off is accounts for the propyl, and the cyclohexane accounts for the 6 carbons in the ring. If the ring has more carbons, it's my parent. If the side group has more carbons, it should be my parent. So in this case, as we were saying before, I can't include the carbons in the ring and carbons out the ring. I mean, I could notice that all these carbons are consecutively bonded, but there's no way to do that. There's no way to make a name that involves that. So I've got 3 carbons in my ring. That could be my parent, or it could be my substituent. I've got 4 carbons outside the ring. That could be my parent, it could be my substituent. I have to look at how many carbons there are. If the group outside the ring has more carbons, it's the parent. If the ring had more carbons, it would be the parent, like it was up here with the cyclohexane. So since I've got 4 carbons outside the ring, 1, 2, 3, 4, the prefix for 4 is but. And so this parent chain is butane. I've got a substituent on one of my carbons constituting the parent chain. That substituent has 3 carbons and it's a ring. So 3 is prop. If it's a ring, it's cycloprop. And since it's not my parent, but rather it's connected to one of the carbons of the parent, I give it the YL suffix. So cyclopropyl is the name of the group, butane is the name of the parent, and the name of the whole molecule is cyclopropylbutane. Any questions about that so far? Alright, so let's take a look at these, see if we can name the substituents. So we already took care of the parent chain in both of these. We'll just review that real quick. 1, 2, 3, 4, 5, 6, 7. So that parent chain was heptane, 7 carbons, all saturated. So we have a side group here. It's 2 carbons long. The prefix for 2 carbons is eth. and it's a substituent. It's not part of the parent, so we call it an ethyl group. Here I've got one carbon attached to one of my carbons from the parent chain. So the prefix for one carbon is meth. And again, this carbon is not part of the parent chain. Anything that's directly connected, or any group of atoms that's directly connected, should have a YL suffix. And I also have one more. Again, this is another 2-carbon chain, just like this one up here. So that one's another ethyl.
I have a question.
Yes, please.
Wouldn't the parent chain be 8 for octane?
Oh, yeah. Good one. That's not a question. That's a correction. Thank you.
You're welcome.
Yeah. Yeah, we did just talk about that, and then I got mixed up. Yeah, so what just happened to me is embarrassing, but beyond that, it does illustrate a common mistake that students make, and I understand why it's a common mistake because I sometimes make it myself, and I just did right now, and that is your brain will get used to thinking of the parent chain as being a zigzag that looks like this, because that's typically how we would do it, right? So if I have a bunch of carbons, I just draw a zigzag and extend the carbons out because that's the most stable arrangement for those carbons. So you really have to try to get away from that instinct and look for the longest chain, no matter where the atoms are positioned in space. So thank you for noticing that. As we said before, I've got 2 carbons here and only 1 down here. So my longest parent is actually going to be 8, even though they're not all spread out in a zigzag. I still want to find the longest chain. So that means I've got a 1-carbon group here, which would be meth or methyl, another methyl, and here I have the ethyl. So the way I had done it before was not correct. That was just a test to see if anyone would catch that. Just kidding, I made a mistake. Okay, so we got 8 carbons there in our parent chain. We've determined what our substituents are. Then we would move on to step 3 in the process. But we want to make sure we've got steps 1 and 2 down. So we'll look at this one again. So here, our longest chain of consecutive carbons was 7, and it was in a ring. So the parent here is octane. The parent here is cycloheptane. 7 carbons is the maximum we can do. We can't include both carbons from the ring as well as carbons outside the ring. So that's our parent. Any carbons that are not accounted for in this name need to be accounted for as substituents. So I've got 2 carbons here and 2 carbons here. Those are both ethyl groups. So F is for 2. The YL suffix communicates that those 2 carbons are not part of the parent chain, but instead connected to some part of the parent chain. This one over here, 1, 2, 3, 4, is a 4-carbon grouping. So the prefix for 4 is bute. Again, these 4 carbons are not part of the parent chain, but one of them is directly connected to the parent chain, so the YL suffix communicates that. So I've got a butyl group and 2 ethyl groups on this cycloheptane parent ring. So it gets more complicated. Sometimes the grouping isn't just an extended chain of carbons. It might have its own branching. So here's my branch point off the parent. So if this was the molecule I was analyzing, I would start here, number it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's the longest chain I can find there. So if we just consult the table, 11 carbons is undec, or undecane if it's fully saturated. So in that example, my parent chain is undecane, but I've got the substituent here that I need to determine a name for it. And when I count the substituent, it's 5 carbons, and the prefix for 5 is pent, and since it's not the parent chain, I would usually put a YL suffix on that. I can't call this molecule pentyl-undecane though. Pentyl-undecane would look different. If I've made 11 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 carbons, and put a pentyl group there, well, 5 carbons would just be 1, 2, 3, 4, 5. If it's fully extended and there's no branching, that's what pentyl actually means. So the word pentyl implies I've got 5 carbons extended with no branching. If there's branching, I need to name it a little bit differently. So when the carbons in the group are not consecutively connected in an extended chain with no branching, what I need to do is to find the longest chain of consecutively connected carbons that's within that side group and name my group based on that. So my parent chain has 11 carbons, it's undecane. My substituent, the longest chain of carbons I can find on my substituent is 4 in a row. So that's going to be butyl. But I still have to account for this. This carbon here isn't connected to carbon 4. If it were just over here connected to carbon 4, it would just be a pentyl. But it's branched off the second carbon of this side group. So what I have here ultimately is a methyl group, a single carbon, attached to a butyl group, which is attached to an undecane parent chain. So I've got layers. I've got this group on this group, which is on this group. And when I've got layers like this, the name has to account for that. So we put the parent chain always at the end of the name and the substituents before that. So if I put butyl undecane, it'll look like this. So there's my undecane. If I put the butyl group on there, it would be 1. It would be 1, 2, 3, 4. So that would be butyl undecane. And I've got this methyl group here on carbon 2 of the butyl group. So if my substituent has something branched off of it, to account for that in the name, I have to tell what number on the substituent that branching is occurring. When I number my substituent, I always have to start numbering on the carbon that's directly connected to the parent chain. So I can't just number this any way I want. Whatever carbon's connected to the parent chain, that's got to be carbon 1, and then I number through the rest of that longest chain I can find there. So that means this methyl group is on carbon 2. And so if that methyl group is there on carbon 2 of the side group, I've got to call that a 2-methyl. The number that comes in front of the name tells me which carbon it's on. But I also have a carbon 2 over here. And so that can be confusing. If I say that this molecule's name is 2-methyl-butyl-undecane, and you just read that name, well then you'd understand that undecane is the parent chain, and you'd make an 11 carbon chain. But then you'd look here and you'd say, okay, this methyl group is on carbon 2. You would assume that the methyl group is here on carbon 2 of the parent chain. So I have to alter the name to make sure that the name communicates that the methyl group here is actually on carbon 2 of the butyl group, which is on carbon 6 of the undecane. So the way to do that is I have to put this whole thing in parentheses. The parenthesis here is communicating that everything in the green box, which is a side group, is attached to the undecane. And that this 2 is the carbon 2 of the side group, not carbon 2 of the parent chain. And then I would need a 6 out here to tell me which carbon this thing in parentheses is on of the parent chain. So this would be the correct name for that structure. The parent chain has 11 carbons, so that's undecane. On carbon 6 of the parent chain, there's this group, and this group's name is 2-methylbutyl, because the group is a 4-carbon or a butyl group, and there's a methyl on carbon 2 of that 4-carbon group. So if you have a substituent on a substituent, that second layer of substituent, its number always has to be inside parentheses with the name of that whole thing, so that I'm not incorrectly thinking the methyl group's on carbon 2 of the overall parent chain. The methyl group's on carbon 2 of what's in parentheses, which is the butyl. What's in parentheses is on carbon 6 of the parent chain. Questions about that? All right, so we'll see more examples of that as we go through. And so that, we just talked about that. So that tells us that the substituent is a 2-methylbutyl. Because it's a 4-carbon grouping, that gives me the butyl. And on carbon 2 of that butyl, there's a methyl group. And I need the parentheses there so I'm not incorrectly thinking that this 2 is referring to carbon 2 of the parent chain. But indeed, it's actually referring to carbon 2 of the butyl group. All right. There are a few common names that you probably want to become familiar with. So if I have a long chain of carbons, and this is my group hanging off, it's got 1, 2, 3 carbons in it, so it's a propyl group. If there's a site of branching there, really I only have 2 carbons in a row, and then I've got a methyl there. So this would be an ethyl group with a methyl attached to it. And the methyl is attached to carbon 1. So in parentheses, similar to what we just showed on the last slide, the naming of this whole group, well, it's an ethyl group with a methyl on carbon 1. So it's a 1-methyl ethyl. That is the IUPAC way of naming this side group or substituent. But almost no one calls it that. You'll almost always ever see it called isopropyl. And so the prefix iso specifically refers to this grouping of atoms where you have 2 CH3 groups on 1 carbon. There'd also be a hydrogen there. This is an isopropyl group, right? It's got 3 carbons, so it's propyl. It's not just a regular propyl, though, because then that would imply the 3 carbons are extended. Since it's a branched propyl, it's called an isopropyl. But this specifically is the iso grouping. So if you see that, just that little Y, that's an iso grouping. It's got 3 carbons, so that makes it an isopropyl. If this here is part of my parent, this is an isopropyl group. A couple other common ones that you would want to be familiar with. Different branching patterns for 4 carbons. So if I have 4 carbons on my parent chain, that's but for 4, and the YL suffix shows me that this is a substituent, not part of the parent itself. If there's no branching, 4 carbons is just a butyl. If there's a site of branching here, I could call that sec-butyl because it's the second carbon of the 4 carbons that's actually connected to the parent rather than the first carbon of the 4 carbons connected to the parent. Or I could call it a 1-methylpropyl because I have 1, 2, 3 carbons that I can count in a row as part of that substituent, so that makes it a propyl. Prop means 3. And there's a methyl on carbon 1 of that propyl. So 1-methylpropyl is the same as sec-butyl. Notice that all the common names just tell you the total number of carbons. And the little prefix in front of that tells you about how those carbons are branched. The IUPAC version is the systematic, standardized way of counting the longest chain of carbons I can in the substituent, naming that substituent, and then any substituent that's on the substituent has a number and a name for it that tells me where on that side group that extra layer of side group is attached. So this is an isobutyl. What do I see here? I see the same pattern that makes that iso pattern. I've got a CH3 bonded to a CH bonded to another CH3. So if I have 3 carbons, that's isopropyl. If I add another carbon, now I have 4 total, that's isobutyl, because but means 4 and prop means 3. Here I've got a tert-butyl grouping. The tert refers to a tertiary carbon. So just write that here. Tert means tertiary, and tertiary means it's bonded to 3 things, like primary, secondary, tertiary. Tertiary means 3 things. So here I've got this carbon is bonded to 3 identical CH3 groups. So that is the pattern of atoms that make something tertiary. So if I were to name it by the IUPAC naming system, though, the longest chain of carbons I can find is 2. So that's why it's ethyl. Eth means 2. On the first carbon of those 2, there's 2 methyl groups. So when you have 2 identical groups, they both need a number, and you need a prefix to tell me how many of them are. There's redundancy built into this naming system. So if this is my parent, this is my side group that's attached to the parent. There's 2 carbons in it, that's why it's an ethyl. The groups that are attached to the side group are both methyl groups. There's 2 methyl groups, so that's why it's called dimethyl. Di means 2. And they're both on carbon 1 of the side group, so that's why I have 1, 1. So I need 2 numbers. Students almost always leave out, well, I shouldn't say almost always, but very frequently will only put 1 number here. So if I just write 1 dimethyl, that doesn't include all the redundancy I really need there. The di does tell me there's 2 methyl groups, but putting only 1 number here, it's not really complete, because I need a number to communicate where every methyl group is. And both those methyl groups are on carbon number 1 of the side group, so it really should be 1, 1 dimethyl to communicate I have 2 methyl groups on carbon 1 of the side group. And then again, that whole thing has to go in parentheses, because otherwise I might start to think that these methyl groups are on carbon 1 of the parent chain, but they're not. They're on carbon 1 of the substituent. A couple common names for 5 carbon groupings. So if my parent chain is longer than 5 carbons, and I number it and I find maybe it's a heptane or octane or nonane or something like that, and I've got this 5 carbon grouping coming off the side of my parent chain, 5 carbons, the prefix is pent, and if it's a side group or substituent rather than the parent itself, I use the YL suffix there. But again, just telling how many carbons there are implies that those carbons are extended, branched out, extended from one another without any extra branching off any of the interior carbons. So there's a couple that you want to be familiar with. Isopentyl, isoamyl is also used sometimes. That one is even older. I don't really hear many people using that name, so I'll probably avoid it. We might use isopentyl. That, again, pentyl implies that there's 5 carbons total. I can't just call it pentyl, because that would imply that the 5 carbons are all extended. But there's branching here, so I'm calling it isopentyl. Notice, that, again, the iso group, very common prefix in organic chemistry because it happens a lot. You see a CH bonded to 2 CH3s, that's the iso. That's what is always present in an iso something. So if those are the only 3 carbons, and that's directly connected to the parent, it'd be isopropyl. If I have 4 total carbons, it'd be isobutyl. If I have 5 total carbons and that iso at the end, that makes it isopentyl. And then the other one, actually just to describe as well how this name comes about. if I'm using the IUPAC system rather than looking at the common name, which is isopentyl, looking at the IUPAC system, I'd number from the parent chain out. The longest chain of carbons I could find is 4, so that's butyl. And I've got an extra methyl group on carbon 3. Not carbon 3 of the parent chain, but carbon 3 of the side group. So this methyl group on carbon 3 of the side group has to be in the parentheses with the whole side group. The whole entire side group name has to be in parentheses if you're going to use the IUPAC naming system to name that substituent that has branching on it. Over here, this substituent, the longest chain I can find is 3 carbons, so it's a propyl substituent. Here I have 2 methyl groups, and they're both on carbon 2 of the propyl. So again, if I have 2 identical things, I need that redundancy. I need a number for each and a prefix to tell me how many there are. 2,2-dimethyl implies that on carbon 2 of the propyl, I've got 2 methyls. And again, that whole thing has to be in parentheses because that whole thing is on the parent chain. And these numbers refer to the site that's in the substituent, not the site of the parent chain. That's what the parentheses help me understand. The neo prefix refers to a carbon that doesn't have any hydrogens. So if you can remember that, there's going to be maximal branching in a neo group. So neopentyl has a total of 5 carbons in that substituent, and there's maximal branching at one of those sites, so it has 0 hydrogens attached to it. So that's a neopentyl. The neopentyl is like the terbutyl, but it's got an extra carbon, right? So if my parent chain is directly connected to a carbon that's got 3 other carbons attached, there's a total of 1, 2, 3, 4. That's terbutyl. If my parent is connected to that same thing, but there's an extra carbon in between that and the site where there's 3 more carbons attached, well, now I've got 1, 2, 3, 4, 5 total carbons, and so that's neopentyl. So a neopentyl is just like a terbutyl, but there's an extra CH2 separating the parent from the site of all that branching. So hopefully that clarifies some of those common names for you. And so the next step involved in this process is assembling the entire name. So once we can name the parent chain and we can find the substituents and name all the substituents, the next thing we have to do is make sure that we number the parent chain so that we can get numbers to communicate where on the parent chain our substituents are connected. Right, so this molecule here is clearly different from the other one. If my methyl group's connected to the second carbon in, it's different structurally than if it were connected to the third carbon in. That means these 2 compounds are constitutional isomers or isomers. They have the same formula, same number of carbons and hydrogens, but they're connected differently. In order to make one into the other, I'd have to break off this carbon from carbon 2, and I'd have to move it over here. I'd have to swap it with the hydrogen that's currently on carbon 3 to make this other structure. So to make one structure into another, if I have to disconnect atoms and reconnect them in a different spot, that's how I make an isomer. But I need a number which locates where on the parent chain the side group is. So if the methyl group's on carbon 2, it's 2-methylpentane. If it's on carbon 3, it's 3-methylpentane. Is there such a thing as 1-methylpentane? There's no such thing as 1-methylpentane. If I try to draw a pentane and then put a methyl group on carbon 1, well, I've just drawn hexane because now I have a 6-carbon parent chain. So some names aren't possible. So you want to make sure you follow the system as carefully as you can. And once you find your parent chain, you have to number the carbons in that chain in the way that gives the substituents the lowest numbers possible. And so that's what we've done here. over here on this 5-carbon chain, I wouldn't number it from this side. I wouldn't call it 4-methyl pentane. I have to number it from the side that gives the substituent the lowest number possible. It's got to be 2-methyl pentane. So when you have a molecule with lots of substituents, you got to find out which side to number it from to give the substituents the lowest numbers possible. So let's look at some more examples. Well, here's another one to illustrate that. So here I've got 7 carbons in my parent chain. So I know the parent heptane. I've got a methyl group connected to that chain. So I know that there's a methyl substituent. So I'll add that in front of the parent chain, the parent name. So the name of this molecule will be methyl heptane. Except the methyl group could have been on any one of these interior carbons. So I have to communicate which one it's on. And in order to do that, I'd start numbering on the side of the parent chain that gives the substituent the lowest number. So I wouldn't start numbering over here and give the methyl group a 6 when I can number on the other side and give it a 2. So the name of that would be 2-methyl heptane. If the methyl group weren't here and it were over here, that would also be 2-methyl heptane. Because if the methyl group were on the other side, then I would have to start numbering from the other side. And if I number 1, 2, 3, etc., I still get the methyl group on carbon 2, so it's still 2-methyl heptane. So be careful about which side you number the parent chain from. And also, as we said earlier, be careful about finding the parent chain properly and getting the longest chain of consecutive carbons, because that's easy to also make a mistake with. Sometimes you might look at all the numbers and you won't know which ones are lower. So in this situation, I've got 7 carbons in the longest chain I can find. If I number from the left to right, I get one numbering system, and my methyl groups are on 2, 5, and 5. So I'd have 2, 5, 5, trimethyl, because there's 3 methyls, so trimethyl heptane. If I number from the opposite side, my methyl groups are on 3, 3, and 6. So which is better? Well, I don't care about the sum of the numbers or the average of the numbers. I care about the first number. If I number from left to right, the first substituent I run into is on carbon 2. That's what matters. If I number from right to left, the first substituent I run into is on carbon 3. And so that's not correct. Whatever side I number from, whatever side gives me the lowest number for my first substituent, that's the correct numbering. So the name of this compound would be 2,5,5 trimethyl heptane. Here's a situation where the first substituent I run into has the same number no matter which way I number the parent chain. So we're still following the steps in the same order. Step 1 is still find the longest consecutive chain of carbons, which is 7 carbons. Step 2, figure out where my substituents are and determine the names of the substituents. So I have a methyl, I have another methyl, and I have another methyl. Step 3 is to number the parent chain from one side or the other to make sure you give the substituents the lowest numbers possible. So if I number from left to right, the first substituent I run into is on carbon 2. If I number from right to left, the first substituent I run into is also on carbon 2. So that's a tie. So then I got to look for whichever numbering system gives the second substituent the lowest number possible. So if I number from left to right, my first substituent would be on carbon 2, but the next substituent I don't run into until carbon 5. The opposite situation, my first numbering from right to left, my first substituent's on carbon 2, but then the next substituent is right there on carbon 3. So that gives the second substituent a lower number than it would have if I numbered from the opposite side. So in this situation, it's only correct if I number from right to left, and when I do, my methyl groups will be on carbon 2, 3, and 6. So the name of that compound would be 2, 3, 6 trimethyl heptane. Again, there's redundancy. I need a number to tell me each of the carbons my 3 methyl groups are on, and I need the prefix to tell me that there are 3 of them. That way there's no question about how many methyl groups there are and what carbons they're on of the parent chain. If you have other substituents other than carbon groups, you want a number from the side that gives the alphabetically preferred substituent the lower number. So here my parent chain has 5 carbons, so my parent chain is pentane. Pent means 5. I've got a bromine on carbon 1 and a chlorine on carbon 5. If I number from the other direction, though, I'd have a chlorine on carbon 1 and a bromine on carbon 5. But since B comes before C alphabetically, I got a number from the side that gives the bromine priority over the chlorine. Later in the semester, when we introduce molecules that have oxygen and different situations like double bonds and triple bonds, the groups will determine which side I have to number the parent chain from based on priorities that we'll have to learn as we go through there. So for now, if you're just dealing with hydrogen and carbon, focus on giving the groups the lowest numbers. If you have a halogen, then the alphabetization of the first letter of the halogen may come into play. But that would only be true if they both get the same numbers either way. So if it's a 1, 5, so I have a substituent on carbon 1 and carbon 5, and over here I also have a substituent on carbon 1 and carbon 5. It's a 1, 5 either way. That's the only situation where the alphabetization is relevant. Right? So for example, if I had my 5 carbon chain here, and let's say I had a bromine here, and let's say I had a chlorine here, and a bromine here. In this situation, I wouldn't number from right to left. If I did, I don't get the first substituent until carbon 2. So even though the bromine takes precedence over the chlorine alphabetically, I still want a number from the side that gives the first substituent I run into the lowest number possible. So if I number from the opposite side, 1, 2, 3, 4, 5, well, I can have the chlorine on carbon 1. If I number from right to left, I don't get the bromine till carbon 2. I don't get any substituents till carbon 2. So the correct numbering in that situation would be to number from the side that gives the first substituent the lowest number possible. That's my tried and true rule. So I want to give the first substituent the lowest number possible. If the first substituent gets the lowest number possible either way, that's the only time when I go to look at the alphabetization. Same rule applies for cyclohexanes or any cyclic compounds. So I got to put the cyclo prefix in there to indicate that my parent chain is a ring. In a ring, there is no beginning and no end. So on a chain, depending on the substituents, I have to number from one side to the opposite side. And so I would number from the side that gives me the substituents first. In a ring, there's no side. There's no one left or right side. There's just the ring. So I can make any one of these carbons carbon 1. If there's a substituent, I want that to be carbon 1, so it'll have the lowest number possible. If there's multiple substituents, one of those is going to be carbon 1, and I'm always going to number toward the other one to give both substituents the lowest numbers possible. So this would be 1,3-dimethyl cyclohexane. Up here, I've got 2 carbons on carbon 1. So this would be 1, 2, 3. This would be the correct way to number this 6-membered parent chain. If I number it the opposite direction, I still get the first substituent and the lowest number, but the next substituent I won't run into until carbon 3. So that's not the preferred numbering. If I can put as many substituents with the lowest number as possible, that's the preferred numbering. So the name of this compound, the parent name is cyclo because the parent is a ring, hex because there are 6 carbons in the ring, ane because all those carbons are saturated. And then I've got methyl groups. I've got a methyl group, 2 methyl groups on carbon 1 and 1 methyl group on carbon 3. So 1, 1, 3, trimethyl cyclohexane. That would be the name of that molecule. Any questions about that so far? All right, so once we number the parent chain, we're going to assign a number to each substituent, making sure we number from the side that gives our substituents the lowest numbers possible. And then we're going to order our substituents in the name alphabetically. And this is the part I dislike. For some reason, they decided that if there are certain prefixes, those are going to be used in the alphabetization. But certain other prefixes are not used for alphabetization purposes. Oh wait, I said that backwards. I'm sorry. Dang. We need the prefix to tell us how many there are, right? So that was why down here we said trimethyl. Trimethyl implies there are 3 different methyl groups, right? I've got 2 of them on carbon 1 and 1 on carbon 3. And I need 3 numbers to tell me where on my parent chain each of those 3 methyl groups are. So if there were other substituents, so let's say there was an ethyl group here. Let's say there was an ethyl group on carbon 2. Then I would have 2 ethyl. And so when we're ordering them alphabetically, the prefixes don't matter. So I would compare the E from ethyl with the M for methyl. E comes before M alphabetically, so this substituent should come before the other substituent in the name of the molecule, the full name of the structure. This is the part that confuses me sometimes. It's hard to remember this, so if you make a mistake on this, I generally don't take off points. But the iso, neo, and cyclo prefixes are used for alphabetization, even though the other prefixes are not. So, do your best to remember that. And we'll try to follow it as closely as possible. But the alphabetization part is not that important, right? If I wrote 1,1,3 triethyl first and then 2-ethyl next, you could still draw the structure. The alphabetization isn't that important for structure. It's more important for listing names of compounds and indices and being able to find them based on listing them alphabetically. But that's not really that relevant anymore now in the age of computers. So here are all the steps involved. Right? We said we're going to find the parent chain first. We're going to identify the name of the parent chain and then identify the name of the substituents. Then we're going to number the chain in a way that gives the substituents the lowest numbers possible. And then we're going to list them in alphabetical order, ignoring all the prefixes except these 3 prefixes when numbering alphabetically. So let's look at some full examples and make sure we can do all the steps. Alright, so here's a molecule. We want to make sure we can name this. So we'd start and try to find the parent chain first. That's step 1. Finding the longest chain of carbons. that are all connected in sequence to one another. So 9 is the longest I can find there. So my parent is going to be no name. So that's the first step. The second step is to find the substituents. So on my substituents, I've got a 2 carbon grouping here. So that's an ethyl. Here I've got 1 carbon, that's a methyl. What's the name of this? Oh, it's 3 carbons, and there's that branching with the 2 CH3 groups attached to 1 CH, so I can call that isopropyl. Remembering that iso happens to be one of those prefixes that does matter alphabetically. Or, if I don't want to use the common name, I can use the IUPAC system, and on carbon 5 of the parent chain, I've got a 2 carbon grouping, which would be ethyl. And on carbon 1 there, I've got a methyl group. So it'd be 1 methyl ethyl, but that would all have to be in parentheses. So isopropyl is the same as 1 methyl ethyl. I can write either one. If I write isopropyl, I pay attention to the letter I for the alphabetization. If I write methyl ethyl, I pay attention to the letter M for the alphabetization. And then one more substituent here on carbon 8. So now I've identified my parent chain. Did I number it correctly? So I might number it initially just to find the longest parent chain I can find. But I always want to check to make sure it's numbered from the right side. If I number it as I have, 1, 2, 3, I don't find the first substituent until carbon 3. If I number from the opposite end, 1, 2, 3, 4, etc., well then my first substituent appears on carbon 2. So actually that's the preferred way to number that. So I want to get rid of some of this and renumber that so we get our numbering system properly here. 1, 2 gives me my first substituent with a lower number than if I had numbered the other direction. My first substituent would have a number 3. So I want a number from the side that gives me the lowest number possible for the first substituent. If there's a difference, I don't even worry about the numbers for the other substituents. I'm only concerned about the first substituent first. Okay, so my parent chain is nonane. I've got a 2-methyl. I've got a methyl group on carbon 2. I've got an isopropyl or a 1-methyl ethyl on carbon 5. I've got a methyl on carbon 6. And I have an ethyl, a 2-carbon group on carbon 7. So now I have to put these in alphabetically, right? So E comes before M or I. So my name, I would write 7-ethyl. I comes before M. 5-isopropyl. You're going to have a hyphen between a letter and a number. And you're going to have commas between numbers. So follow that as well. So I've got ethyl on 7, isopropyl on carbon 5 here. And I've got a methyl on 2 and a methyl on 6. So I need 2 numbers. I need the 2, comma 6. This tells me that whatever name I'm going to put here, there's one of those on carbon 2 and one of those on carbon 6, and that is a methyl. And then you don't need any punctuation of any kind between the last substituent and the parent name. So 7-ethyl, 5-isopropyl, 2,6. Oh, I forgot my prefix here. If there are 2 of them, I need a prefix to confirm, even though it's redundant, how many there are. So if I've got 2 methyl groups, I really need to put di-methyl there, nonane, for the name of that molecule.
If it's dimethyl, would you put that in front then, since it is the letter like Di?
No, that's a good question, but the people who came up with this committee of chemists, they wanted to make it as hard for you as possible, Ethan. So we only alphabetize these letters, in these prefixes. Any other prefix like di or tri or sec or tert, those don't count alphabetically. There's only 3 prefixes that count alphabetically. So since the di doesn't count alphabetically, but the iso does, that puts the iso before the methyl in that particular name. All right, so make sure you practice up on drawing compounds based on naming compounds based on their structure, as well as drawing compounds based on their name. This is usually much easier for students because once you've got the name, it really gives you all the structural information on how to connect everything. So I start at the right-hand side because that's my parent. Right? We put the parent chain in, the parent chain last in the name. So I look there first. So cyclohexane is my parent. So I start by making a 6-membered ring. Right? Hex means 6. Cyclo means those 6 carbons are connected in a ring. And then I just look at my substituents one by one and put them on. Right? So on carbon 1 of the ring, I've got a tert-butyl. So tert-butyl has 4 total carbons. 1, 2, 3, 4. And this one here is the tertiary one. It's bonded to 3 identical things. On carbon 2, I've got an ethyl. So I put a 2-carbon grouping on carbon 2. Meth means 1. So on carbon 4, I've got 1 extra carbon. So put that in there on carbon 4. On carbon 3, I've got cyclopentyl. So on carbon 3, I've got pent, which means 5, but they're in a ring. So I have to connect a ring of 5 carbons. So that would be the structure for that name. Any questions about those? Alright, so here were the first couple quiz questions for today. Very similar to what we just did, just different structures or names. So in this case, my structure up here, I want to find the parent chain first. So I'm recognizing now, based on what we just talked about, when I number my parent chain, the longest chain, I don't want to number from this side because I won't reach the first substituent until well into the structure. So if this grouping down here is part of my parent chain, I want to number from the other side. So let's see, 1, 2, 3. If I number up into here, 4, 5, 6 is the longest I can do. If I number down here, 1, 2, 3, 4, 5, 6, 7, that's longer. So that has to be my parent chain. So 1, 2, 3, 4, 5, 6, 7. That's the longest chain of carbons I can make. And numbering it from the left to the right allows me to get to my first substituent on carbon 2, whereas if I number it up from over here, 1, 2, 3, 4, 5, my first substituent wouldn't be till carbon 5. So my parent chain here is heptane. Now I've got to name these substituents. On carbon 2, I've got a single carbon. 1 carbon is meth. So that's a methyl group. So it's 2-methyl. On carbon 3, I've got this branched thing here. And this doesn't match up with any of the common names we talked about. So my only option with this is to name it as an IUPAC substituent. So to do that, we said the first carbon that's directly attached to the parent, that carbon has to have a number 1. So it's got to be carbon 1 of the side group. And then I want to find the longest chain of carbons that I can that's part of the side group. So I could number 1, 2, 3 here, or 1, 2, 3 there. It's the same thing. Either way, it gives me the same name. So now, this is a propyl side group. It's got 3 carbons in it. But there's more side groups on the side group. I've got a methyl on carbon 1 and an ethyl on carbon 1. So my whole side group has to go in parentheses. This whole thing is on carbon 3 of the parent. So whatever this thing's name is, it's going to be on carbon 3 of the parent chain. So really I've got a propyl group on carbon 3 of the parent, right? Here's my propyl group on carbon 3 of the parent. But the propyl group has stuff on it. The propyl group has a methyl group on carbon 1 of the propyl and has an ethyl group on carbon 1 of the propyl. Ethyl comes before methyl alphabetically. So on the propyl group, on carbon 1 of that propyl group, there's an ethyl. And there's also on carbon 1 a methyl. So the name of this whole thing isn't 1 ethyl, 1 methyl propyl, and that whole thing is on carbon 3 of the parent chain. Alphabetically, it has an E versus the M here for the group on carbon 2. So the full name would be 3, 1 ethyl, 1 methyl, propyl. That's the group that's on carbon 3 of the parent chain. On carbon 2 of the parent chain, I have a methyl. So I ran that space to write it like this. That accounts for every carbon in the structure, and by default also counts for every hydrogen, since we know there is enough hydrogens to complete the noble gas for each carbon atom. The way that the name is constructed accounts for all the branching. If I just saw the name, I could recreate that structure. And so this is the correct name for that molecule. The second part of this question is much easier. Again, when you're given the name, start with the parent chain and draw that out. So nonane has 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the other numbers tell you where on that 9 carbon chain things are going to be connected. So if I just number from left to right, and then follow what the name tells me to do, on carbons 1, 2, 6, and 7, I've got tetra, which means 4 bromos, or bromine atoms. So I've got a bromine on carbon 1, I've got a bromine on carbon 2, I've got a bromine on carbon 6, and a bromine on carbon 7. Then on carbon 4 of my parent chain, I've got this stuff. So again, these numbers are inside parentheses. This 1 and 2 are not referring to carbons 1 and 2 of the parent chain. They're referring to carbons 1 and 2 of this ethyl group. That happens to be on carbon 4. So when I've got something in parentheses, I look to the end of the parentheses to find the main thing that's attached to the carbon that that thing in parentheses is connected to. And so on carbon 4 of the nonane, I've got this ethyl group. And on that ethyl group, if I number, I have to start numbering with the carbon that's connected to the parent chain. On carbon 1 of the ethyl group, I've got a chlorine. And on carbon 2 of the ethyl group, I've got a chlorine. So that would be one way that structure could be drawn. So if you're rotating around some of these bonds, it's still the same structure. But if you put one of your bromines on 3 instead of 2, obviously that's not correct. It's a different structure because the name tells you which atoms everything's connected to. Questions about those? Alright, so sometimes you run into some bicyclic compounds, and these are weird. These are really weird shapes. It's hard to imagine them three-dimensionally, so I would definitely recommend maybe making the models of these if you want to take pictures of your models and share them with me, or bring them into the lab and talk about them. A bicyclic system has multiple rings fused together. So if I have a single cyclohexane, I could fuse another ring to that by maybe making another 6-membered ring. So that's a fused ring system. Oftentimes, one area of a ring might be bridged to another area of a ring with some number of carbon chain there. So this is kind of a better representation than this. It's more representative of what it looks like in 3 dimensions. So if I just communicate to you how the carbons are connected, this carbon is connected here. This carbon is connected to this one, obviously, and to this one. So notice here, these lines aren't totally overlapping, and that's to communicate that this single bond between, I'll number this carbon 1 and 2. Carbon 1 and 2 are connected, but 3-dimensionally that bond is behind the bond between the ones I just happened to number 3 and 4. Right? So there's no carbon here where these lines intersect. That's why we're not showing them actually touching. We're showing the bond between 3 and 4 over top of the bond that's happening behind there that happens to be between 1 and 2. So if you have a bicyclic compound, which you may have to deal with, naming, there's some modifications to the naming system that you need to look at. So the first thing you would do for a bicyclic system is to count the total number of carbons. So if I have this bicyclic system or this one, counting up the total number of carbons, 1, 2, 3, 4, 5, 6, 7. Over here, 1, 2, 3, 4, 5, 6, 7. So both of those have 7. But they're clearly not the same structure, right? Things are connected differently. They have different shapes, different numbers of rings, right? This one has a 6-membered ring at the base, and then a 5-membered ring over here that I can highlight. This one has a 4-membered ring over here. So it's different structurally. So even though they have the same number of carbons, we have to have a system that communicates about what their structural differences are. So here's a system for bicyclic compounds. So they're going to have the same parent name, which is bicycloheptane, because they're both bicyclic or fused ring systems, and they both consist of 7 total carbons. So then we use these numbers in the brackets. This is different from anything we've talked about yet. We use these numbers in brackets to communicate about how many carbons there are connecting the bridgeheads. The bridgeheads are the carbons where the rings are fused to one another. Right? These carbons where multiple bonds come together and act to fuse the rings together. So in this structure, I'm counting not the bridgeheads themselves, but how many carbons the loop is between that bridgehead that makes it all the way back around to the other bridgehead. So from here, 1, 2, 3, back to the other bridgehead. So that loop has 3 carbons in it, and that's where this 3 comes from. Looking at the other loops from the bridgehead back to the other bridgehead, going up here, there's 1 carbon. Then next, I'm right back to the bridgehead again. So that loop only consists of 1 carbon. And then the third loop, again, is only 1 carbon long, then right back to the bridgehead. So bicyclo-3,1,1 heptane indicates I've got 7 total carbons fused together in a fused ring system, where one loop between the bridgeheads has 3 carbons and the other 2 loops between the bridgeheads both have 1 carbon. And that's different from bicyclo-2,2,1, because in the 2,2,1, from the bridgehead back to the other bridgehead, this loop has 1, 2 carbons, back to the bridgehead. This loop has 1, 2 carbons, back to the other bridgehead. And the other loop has 1 carbon, and then down to the bridgehead. So that'd be a 2-2-1 instead of a 3-1-1. And so those are similar, but the difference in the way that they're connected and constructed is accounted for with these numbers in the name for the molecules. So what if they're substituents? If there are substituents, then I have to follow the rules for numbering the parent chain so I can give the correct location for the substituent. So once so let's take a look at this one here. So I've got a CH3 group or a methyl group attached to this carbon. So I want to put the name together for the structure. So before I do anything, I want to count the total number of carbons in just the rings, the fused ring system. So the substituent I'm not using obviously as part of my parent name. Right? So we're still following the general strategies. First I want to determine the parent name, the parent chain. So here I've got 1, 2, 3, 4, 5, 6, 7, 8 carbons. So it's a bicyclo octane. 8 carbons. It's a fused ring system. So it's a bicyclooctane. And then the numbers that go in the brackets will depend on how many carbons there are in these loops connecting the bridgeheads. So the longest loop here from this carbon to the other bridgehead is 1, 2, 3 carbons back to the bridgehead. The second longest loop between bridgeheads is only 1, 2 carbons long, and then back to the bridgehead. And then the third loop is only 1 carbon long and then back to the bridgehead. So the name of this compound, if the methyl group weren't here, if the CH3 weren't here, it would just be bicyclo-3,2,1-octane. This methyl group is here though, so once I determine the parent chain, then just like before, I've got to number the parent chain in a way that gives the substituent the lowest number possible. But there are some rules for that. And let's see if they're outlined here. They're not. So let's outline these rules. So actually let's see. Oh, I think they are here. Okay, they're here, right. So when you're numbering a bicyclic system to determine what number the substituent should get, you have to start from a bridgehead. No, that's up here. Sorry. Start from a bridgehead carbon. And you have to number into the longest loop first. Right, so if I'm looking at this compound, I can't start number 1 here because it's not a bridgehead carbon. These are my bridgeheads. That's where the rings are fused together. I'd like to start 1 here because that would give the substituent the lowest number possible, but that breaks the rules for numbering the parent chain in a bicyclic system. I have to start with with one of my bridgeheads, and I have to number into the longest chain first, whether the substituent's there or not. Then I can number into the second longest chain, and then the third longest chain, and so on. So I have to start numbering at one of my bridgeheads. So for this molecule, there's 2 options, because I've got 2 bridgeheads. If I start at this bridgehead, I have to number into the longest chain first, so 1, 2, 3, 4, 5, and then numbering into the second longest chain, I have to keep going from there, 6, so this will be a 6-methyl. If I start from the other bridgehead, which I could possibly do and need to consider, I still have to number into the longest parent first, so 1, 2, 3, 4, 5, then continuing from there, 6, 7. The methyl group wouldn't be counted until 7. So I want to number, I have to follow these rules. I have to start numbering carbon 1 on a bridgehead. I have to start numbering into the longest loop first between bridgeheads. And then if I keep going, whichever bridgehead I start on, that gives me the lower number for my substituent is the correct numbering. So this would be 6-methyl bicyclo-3,2,1-octane. This one here would be 8-methyl bicyclo-6,2,1-octane, because I still have to follow the same 2 rules. I have to start on one of my bridgeheads, I have to count into the longest loop first, and then I have to count into the second longest loop, and then I count the third longest loop. So there's no way to give the methyl group a lower number than this when it's on the shortest loop between bridgeheads, and so that's why it's going to end up being 8-methyl bicyclo-3,2,1-octane. As we were saying at the beginning, the IUPAC system is very complicated. We're only going to be touching the tip of the iceberg on this. The system involves tons and tons of rules that account for a variety of different types of bonds that we're never even going to see. So here's just one example. Here's the IUPAC name for this molecule. Right, so who wants to even say this name out loud? Probably nobody. But the name accounts for all the connections here, and all the numbers refer to positions of atoms. Here's the name of my parent chain. So what is this? I mean, we won't even get into these types of structures. So we're only scratching the surface here. And in reality, even though this is technically the correct IUPAC name for this structure, it's not the name most people know the structure by. Most people know the structure by its common name or its commercial name. So you got to realize there's lots of different names for things. Typically, if the molecule is relatively simple, like this one here, it probably would be named by its IUPAC name. So the IUPAC name is used a lot for relatively simple molecules. You won't just want to be aware when they get more complex, those names aren't usually used. So we're not going to worry about trying to get too deeply into the IUPAC naming system. So we were talking about isomers early in the semester. We want to just mention here how sometimes it's hard to tell if molecules are isomers or not. One way to help you with that is to look at the names of the compounds and see if they have different names, right? So isomers have to have all the same atoms, which means they have to have the same formula. So if I'm asking you what's the relationship between two structures, the first thing you want to do is check out their formulas. Count how many carbons there are. Count how many hydrogens there are. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Do the same thing on both structures. If they have the same formula, because they have the same number of every type of element present, they may be identical or they may be isomers. If they don't have the same formula, they don't have any real relationship. So that's the first thing you always want to check. If they have the same formula, they may be isomers or they may be identical. So then you want to look for differences in how the atoms are connected. So clearly here you can see the difference. Right? I've got 6 carbons all extended in a chain versus 5 carbons in a chain, and then the one that was on the end is now here bonded to the second one in. So clearly there's a different connection there, and so they're not the same, which makes them isomers. Sometimes it's not easy to tell. Right? So between this structure here and this one, what's the relationship? Are they isomers? Well, they both have C6H14, C6H14 for both. They look similar. Are they identical? So isomers are not identical. So there's a couple ways you can look to see if they're identical. One is you can make a model of both and see if the models superimpose, see if they look exactly the same and they could lie right on top of one would lie right on top of the other. Or you could just name them both. And if they have the exact same name, they're not isomers. So as long as you've named them correctly, if they have the same name, they're actually identical. So if I were to name this structure, the longest chain of carbons I could find would be 5, so it'd be pentane. There's a methyl group on carbon 2, so it'd be 2-methyl pentane. Looking at the other structure, if I were to name it, I would have to number from this side to give the substituent the lowest number possible. And when I do, I would find that's also pentane with a methyl group on carbon 2, so it's also 2-methyl pentane. And so if I can't see visually with my eyes that these two structures are identical and one is just like a flipped over version of the other, naming both of them is another way to kind of double check to see if they're the same or to see if they're different. And so this one's name is hexane because it's got 6 carbons with no branching, and this one's 2-methyl pentane, clearly different names, alerts me to the fact that they're not identical or that they are indeed isomers. There are other constitutional isomers for C6H5, C6H14. So let's see if we can draw some more of these. So recognizing isomers is one skill, and naming them and seeing if they have the same name can help you do that. Drawing isomers is an entirely different skill. So if I want to draw another isomer of this, what can I do? Well, instead of having this methyl group on the end, which would have made the original structure, I could have put it one carbon over, so I could draw this structure. So this one was 2-methylpentane. This one is 3-methylpentane. So those are different. They're isomers. I can't move the methyl one over though, because if it were here, it would be 2-methylpentane just like that one. So that wouldn't create a new isomer. So what else can I do? Well, typically when you're drawing as many isomers as you can for a formula, you want to look at varying degrees of branching. So by taking one carbon off of the end and moving it over here, that gave me an isomer because I created a site of branching. Or if I moved it here, that gives me a different isomer because I created the branching at a different position. So if I want more isomers, I can create more branching. So I could take another carbon off the end and put it somewhere. I could also put it on carbon 2. So that would give me something like this. What would the name of that be? Well, here the longest parent chain I can find is 4 carbons. And there's 2 methyl groups on carbon 2, so that'd be 2,2-dimethyl-butane. Clearly a different name from 2-methylpentane or 3-methylpentane, but still has 6 carbons and 14 hydrogens, so it's an isomer of the other ones. I could take those 2 methyl groups and move them over here, but that doesn't really create an isomer because now I just have to number from the other side and I still have 2,2-dimethylbutane. So that's not a new one. That one's identical to this one. So if I'm trying to draw unique isomers, I need to make sure they're not the same as the ones I already drew. So if I want to create another one, create more branching. So here I could take another carbon off and move it to a site and create more branching. So if I, instead of having 4 carbons in my chain, I could have 3 and do more branching. How does that look? Hopefully as soon as I did that you were repulsed by that because it looks so disgusting. Yeah, can't have a 5 bonded carbon, so that definitely doesn't work, right? So at least my structure has to be, at least it's got to be somewhat stable. So the other option is when I went from this structure to this branch structure, I didn't have to put my 2 methyl groups on the same carbon. I could have put them on different carbons. So there's just through trial and error finding all the different options. So instead of having both methyl groups on carbon 2 and being 2,2-dimethylbutane, here I've got one of my carbons on carbon 2, or one of my methyls on carbon 2 and the other on carbon 3. So that would be 2,3-dimethylbutane. So the isomers for this formula are hexane, 2-methylpentane, 3-methylpentane, 2,2-dimethylbutane, and 2,3-dimethylbutane. Right, so there's some problems in the textbook that help you practice that skill as well. The number of isomers dramatically increases the more carbons I have. That's not surprising. Right? If I don't have very many carbons, there's only one way to connect them. If I add another carbon, now I can have them in an extended chain, or I could have branching. So if I have a whole bunch of carbons, well, I could extend them all out. I could have all 9 carbons all extended. Or I could do lots of different branching. Right? I could take one off and put it on any one of these inside. I could put an ethyl group on. I could take 2 carbons off and make that an ethyl group somewhere. And so there's lots of different variety of branching. And that gives me a situation where I get exponential increase in the number of possible isomers when I increase the number of carbons. So just be aware that if I give you a lot of carbons, you probably won't be able to draw all the isomers. I wouldn't expect you to. I might, expect you to draw a couple different isomers, but you want to practice that skill so you can come up with isomers and demonstrate you understand that when molecules are identical and when they're not, based on their names or based on their branching. So here's just an example where you can take a look at this. Looking at these two structures here, we want to try to determine what their relationship is. So if you have a model of this one, you can work with your model that you have on hand. The question is, are these two structures isomers? The first thing I want to check out is, do they have the same formula? Right, so maybe I want to draw in all the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there's 1, 2, 3, 4, 5, 6 carbons and 14 hydrogens. Same thing here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So they have the same formula. That means they're either identical or they're isomers, one or the other. And so there's really two ways to determine which is the case. I recommend you do both. That way, if you get the same answer from both methods, you can be even more confident that your answer is correct. The first way is to name them. Well, it doesn't matter what order we talk about them in. Naming them is really pretty straightforward as long as you can name things correctly. So if I were to name this based on what we just talked about today, I've got pentane as my parent chain, and I've got a methyl group on carbon 3. Naming the other structure, 1, 2, 3, 4, 5, or if I number from the other side, 1, 2, 3, 4, 5. Either way, my parent chain is 5 carbons long, and either way I number it, I get that methyl group on carbon 3. So these two structures have the same name, which tells me that they are identical. I want to confirm that by making sure that they're also superimposable. Superimposable means that if I had both structures in my hands and I could just lay one right on top of the other, everything would line up perfectly. So looking at them as is, they don't really look superimposable. I can't just take this molecule and slide it over on top of the other one and have everything line up. So that's why it's so helpful to have a three-dimensional model, because you can flip the model over in space, you can rotate around the single bonds, and much more easily than on paper, you can usually see if the two molecules line up next to one another. So what you'd want to do in that instance is make one model, let it sit there, make the other model, and then work with one or the other and see if by rotating or flipping it over you can make them look identical or superimposable. So here's what you could do to do that. So if I've got this structure here, just recopied it. I can do a bond rotation. It's got to be a single bond. I can't rotate double or triple bonds. I can only rotate single bonds. So here I'm rotating this bond here. Right? So this carbon here, these two bonds are in the same plane. If I rotate this bond, it's going to take this, it's going to flip out of the plane down into this position down here. So rotating a single bond happens naturally because the single bonds don't really give much resistance to rotation, especially at room temperature. Then it's just a matter of rotating this in space. Right? So if you made your model with this one, just experiment a little bit with what you're working with in your hands right now. Just rotate these bonds, and you can see this methyl group kind of flipping around like a propeller. So if you flip it down into this position, your molecule now looks like this. And now you can just rotate it in space about 60 degrees or so, and it'll look like this, which is exactly the same as the other model. So you should be able to show the two structures are identical by rotating them around in space or rotating around single bonds. if they have the same name. It's kind of a way of double checking your work. Which method is better or more sharp for surefire method? I would say both. It's easy to make a mistake in either one. Sometimes people make mistakes when they're naming compounds. I made one earlier. Sometimes people make mistakes when they're trying to look at whether these things are actually superimposable in 3 dimensions. And when we get into chapter 5, you're going to see how easy that is to make mistakes in those situations. So I would definitely recommend naming the structures and making their models. And you're allowed to bring your model kits to lab when you're working on exams. You're allowed to use your model kits. So I would practice up with that a lot and get used to both of those methods and when you're trying to determine the relationships between structures. So far, what we've talked about, if 2 structures have the same formula, they're either identical or they're isomers. When we get into chapter 5, there's going to be more options. Molecules could be identical, they could be isomers, but within the category of isomers, there are more possibilities. There's constitutional isomers, there's enantiomers, and there's diastereomers. And when we talk about those concepts, it's going to be much better for you if you've already practiced naming compounds and making models and looking at them 3-dimensionally and seeing what the relationships between structures are. When we add more relationships, you'll be able to build on what you've already practiced instead of kind of starting from scratch and being overwhelmed with all the different relationships that could possibly exist. So this was the other quiz question. So I want to look at both methods here. So if you have your model kit, if you had a chance to make this one, you would probably be able to make a model of both and show that they're superimposable. Alternatively, we could name them. So if I were to name this one, I'd find the longest chain of carbons, which would be 7. So its parent name would be hept for 7, ained because it's saturated. And I got a methyl on 2 and a methyl on 5. So it'd be 2,5-dimethyl heptane. If I look at the other structure, I would find the same thing. So sometimes people make mistakes. If you make the mistake of numbering from the other side, you might think, well, maybe they're not isomers because this one looks like it's 3,6-dimethyl. So that's why it's also good to use both methods. So if you made that mistake, you might recognize that you made it, and you might say, well, I can't number from this side because I don't get the first substituent until carbon 3. I've got to number from the other side because then I get the first substituent on carbon 2, and that's the correct way to do it. And when I number from that side, I can see I've got a methyl on carbon 2 and a methyl on carbon 5, so I still get the same name. So these 2 structures are identical. They have the same name. They're also superimposable. So if I want to look at that, the ability of them to be superimposed upon one another, that would take some flipping and moving. It's much easier to do with the model than on paper. So if I flip this one over like a pancake, it would look like this. If I flip it over again, it would look like this. This line right here, don't ignore that. That's just an artifact of PowerPoint being terrible. So I'm flipping this over to try to match things up. So I've got this part of the structure kind of matched up with this part of the structure. So then I got to rotate this bond so that the other part will be flipped up. So if I rotate this bond here, this grouping will then flip up here. And then the 2 structures will look identical. So by flipping the structure over and rotating the bonds, I can get one to look exactly like the other. And that confirms my conclusion by showing that they had the same name, that they are actually identical structures. It's way easier to do with the model. If you didn't follow what I just did on paper, that's not surprising because it's difficult to both explain and see in 2 dimensions. So again, that's why I encourage you to work with the models often. So here are the bullet points for what we did today, and this stuff will be on the next exam, which if you're having an exam tonight or Monday, it's not going to be on that exam. It will be on the exams the following week, so starting next Tuesday. So make sure you practice up there. There's lots of examples in the textbook to practice related to this content. So let me know if you have any questions about that. And then on Tuesday of next week, we will continue with Chapter 4. And we're going to be getting into some structures. And we're going to be looking at their energies or stabilities as they rotate around, right? So we just showed that I can rotate single bonds. I can flip molecules over in space. When I rotate the bonds in this way, this is a problem because these hydrogens here and the hydrogens here, I mean, these are orbitals full of electrons, and if they get too close, cause a lot of repulsion. So the most stable version of a structure is where it's more elongated and stretched out, and we're going to see examples of that, talk about that in a lot of detail on Tuesday. So check out the videos related to that. In addition to the videos there, if you look on Canvas, I just wanted to point out that I made some of my own videos. Most of them are very short. They're all less than 10 minutes. And they correlate with some of the stuff we're going to talk about on Tuesday, which is day 9. So if you scroll down to the lecture recordings, so our standard lectures, our 2-hour lectures are here. And then down here, on some of the specific slides on day 9, I did an extra video explanation with a model because I wanted you to be able to see with the model what those molecules look like and how their energies are affected by the ways that they rotate around in space. So feel free to watch those before Tuesday as well. Or if you don't watch them before Tuesday, I would definitely recommend that you watch them right after the lecture on Tuesday so that you can benefit from that explanation, since I can't really work with the models in front of you guys in person without a video lecture. So that's basically where we're at. Any questions about anything? Alright, y'all. Well, if you want to stay on for a little while, I'm going to stop sharing my screen, but if anyone does have any questions, I'll stay on I'll stay connected with my voice so that we can deal with any issues or questions that you might have.